Hello, so today we are going to continue on this Leetcode problem, which is part of Leetcode Daily Challenge, matrix diagonal sum. So with this problem, we have a matrix, and we want to return the sum of the matrix diagonals, okay? And basically, what they mean by diagonals, plural here, is that it's both the primary diagonal and then the other side, which is the secondary diagonal, okay? So this one and this one. And so and we want to return just the sum of the elements. So for example, here it's 1, 5 plus 9 for this side here, and then 3 plus 7. Now you may say, why not? We don't want to add 5 twice, so we already added it, so we don't add it again. And then the total of those is 25, okay? And so that's pretty much the problem here. Now, how do we tackle it? The length is up to 100, and so we should be able to traverse the matrix cell by cell if we need to. So yeah, let's see how we can use it. Okay, so let's see how we can solve this. So let's see the first example first and see how it's done. So 0, 1, 2, 0, 1, 2. So you notice here for the primary diagonal, right? These values here have I equal to j, so the index of the column is the same as the index of the rows. So you can see 0, 0, 1, 1, and 2, 2 for this one, okay? And similarly, if we try for a little bit of a bigger matrix, just to show you the idea here, same thing. You can see this is the primary diagonal, and this is 0, 0. This one is 1, 1, this one is 2, 2, and this one is 3, 3. So definitely, this is also just a known formula, but just in case you didn't know, you could try it on examples. So the primary diagonal, it's going to be just the values at matrix of I, and we can just take I from 0 to n minus 1, okay? Now what about the secondary diagonal? So the values here, okay? This one and then this one. Of course, this one we want to count it only once. And then here it's going to be this one, this one, this one, this one. And so one thing you notice here is that even if you didn't know about this formula before, it's 2 plus 0, right? 2 plus 1, right? And then 2 plus 2. 2 plus 0 here, the sum, and then here is 1 plus 1, and then the other one is this one, which is 0 plus 2. So you can see here this I plus j are equal, okay? And so you can notice here the sum is actually equal to n, the n being the length of the matrix for an n by n matrix, right? So we could use that to obtain the secondary matrix values. And so that's the idea that we'll use here, which basically we can just, the first solution, we can just like traverse the matrix by I and j, and then if the indices, right, if I is equal to j, right, which is this case here for the primary diagonal, or the sum is equal to n, which is the case for the secondary diagonal, then we immediately add that to our total, okay? And this solution would be of n squared, because we will check all the cells in the matrix, okay? And so that's one solution, but can we do better? Can we do better than O of n squared? And the answer is yes, but how? Let's think about this a little bit again. So let's take this one here. So we already know that for the primary diagonal, we can just take the matrix of I and I. So for this, we don't need to traverse all the cells. We can just do it for I in the range of n. Okay, and then to our total, we could just add this. Now, what about the secondary diagonal? That's where it's a little bit of a problem. So for the secondary diagonal, how do we get the indices? You can notice something here is that, so for the first index, it was 0, 2. For the second index, it's 1, 1, right? For the third index, for the third one, it's 2, 0, okay? And so here you can see there is some sort of symmetry between the value on the primary diagonal and the one on the secondary diagonal, okay? But it's a little bit hard to see with this example. So let's take this one. So you can see the first one is 3, is 0, 3. The second one is 1, 2. The third one is 2, 1. The last one is 3, 0. Okay. So again, here you can see if we put the I values, so this is the I and this is the J. Okay. And so one thing you notice here is we can actually just, the J value, right, is just equal to n minus I minus 1. Because if we just replace, let's say, so for example, for the first one here, so you can, if we apply this, then for example, for the first one, let's just put this up here. And let's see here. So for the first one, J here should be equal to, n is equal to 4 in this case, right? In this case, n is 4. So it's going to be 4 minus I, which is 0, minus 1, which is 3, and that's the case, right? And then G here, this is going to be 4 minus I, which is 1, minus 1, which is 2. And then here, J is going to be 4 minus 2, minus 1, which is 1, which is valid. And then here, J is going to be 4 minus 3 minus 1, which is 0, which is valid. So you can see it does work with these values. But also, if you just look, right, this is I, right? We want to subtract the same thing to get the symmetry, okay? And if I here, we want to subtract it also to get the symmetry. So that's sort of the idea of this solution. So here it means also we can just add the matrix at I, and what is J? J is just n minus I minus 1. Okay, so we could use this formula now, except there is one other caveat to think about, which is if we apply this formula, we add both I and I n minus J minus 1, we will add this 5 twice. Okay, we'll add it first because it's 1, 1, and then we add it also because it's 1, and then n, which is 3, minus 1 minus 1, right? And so we'll add it twice. And so, and you can see here, in this case we added it twice, but in this case there is no common cell between the primary diagonal and the secondary diagonal. So if you try with more examples, you'll notice that primary and secondary diagonal have a shared cell only in the case where n is odd. And that's actually valid in this case because here n is equal to 4, which is even, and we saw there is no shared cell. But here n is equal to 3, and that's odd, there is a shared cell, and this is actually more general. You can try it on more examples. And so in this case here, we want to subtract only if n modulo 2 is different than 0, which means it's odd. We want to subtract the center cell because we added it twice. And so to do that, we just remove the center cell, which is just in this position and this position, which is n divided by 2. And so this is n divided by 2, n divided by 2. Okay? And this should give us the middle cell. And we subtract it, and then at the end we can just return this result. Now, this solution is just we are doing one loop over the rows indices, so it's O(n), and so it's a lot better than this solution, which is O(n) squared. Okay, so we're not going to do this solution, but you can try it on your own. We are just going to implement this optimal one. Yeah. Okay, so here is the solution we saw in the overview. So we just have the total or the result that we need to return. And then we go through the I indices from 0 to n minus 1. And then we add first the primary diagonal and then the one from the secondary diagonal. And then if the matrix length is odd, then we want to remove the center cell because we added it twice. And so we want to remove it once so that we keep it only once. And then at the end, we return the total. So pretty straightforward there. Let's submit. And this passes our test cases. Okay. Yeah, so that's pretty much it for this problem. Please like and subscribe and see you on the next one. Bye.